So welcome. We're going to do the next part. We've done basically the electricity, the electrostatics bit. Now we're going to do, if you like, the magnetism bit in a bit more detail. We've done some of the magnetism, but we're going to do the electromagnetism bit more and more. Because in the end, we have electromagnetism. The two are linked together. The two systems, the two force systems are linked together. So we're going to now start talking about how we can see the effect of changing magnetic fields on coils. In the past we did put a current through a coil and get a magnetic field. Now we're going to have a changing magnetic field around a coil. It causes an EMF which causes a current. So if you like, it's the opposite system. And this is run by Faraday's law. And so we're going to talk about Faraday's law. We're going to talk about a thing called motional EMF, Lenz's law. Those three kind of go together. Then we have these couple of things at the end which are kind of like pointing you in the direction you're going to go if you do EE or you do physics, and that is the generalized form of Faraday's law and Maxwell's equations with the Lorentz force equation. And again, I don't go much into those because they're like, they're the next step that you need to go. We don't do anything with them. We just say, oh, look. So we take a coil, a loop of wire, let's say a single turn coil, a loop of wire, and we connect it to a galvanometer, and we move the magnet backwards and forwards, and what we find is that while ever the magnet is moving, we see a current flowing through the system. How do we tell? Because the galvanometer needle switches backwards and forwards. Remember on the electric field lab, the galvanometer moved whenever there was a current flowing one way or the other when you plotted out the electric field. So in this one, whenever there's a current flowing through this circuit on the left-hand side, then you'll see a deflection in the needle. And if the current's flowing one way, the needle will go to the left, and if the current's flowing the other way, the needle will go to the right. And what we noticed about this is that, ironically, when the magnet is stationary, even if the magnet is right in the coil, we don't get any current flow whatsoever. It's not about the strength of the magnetic field. It's about the rate at which that magnetic field strength changes in time. So it's not a very straightforward kind of relationship. And we can get a magnet and a coil, and we just move the thing backwards and forwards, and we create an EMF. We create a current, and there's an EMF associated with that. And you might have seen these flashlights where you can shake the handle and then you turn the flashlight on, or you might have seen the emergency wireless where you crank the handle and then it gives you wireless for so long. And in essence, this is exactly what a generator is doing. When you buy gasoline, you put it in a generator. The gasoline is running a handle which turns a coil inside a magnetic field which releases electricity. And it's the same as the power station does. The power station just does it on a bigger scale. You're using coal or oil, and you're making steam which causes a turbine to spin. That's just replacing you as a way of cranking the machine. And all that does is it turns a coil inside a magnetic field, and that creates electricity. So this is the principle of generators. We don't have to use a bar magnet. We can actually use an electromagnet. And so this next diagram, this is from the book, and they switched it. I don't know why they switched it, but basically we have the generating side now on this side, and we have the receiving side on that side. And what we see is when we close this switch, what we get, let me get my pen out and then I can, when we close this switch, what we get is we get a momentary sudden increase in current flow. That causes a rate of change of magnetic field strength which is high until it reaches a steady value. So if I was to plot current versus time in that first thing, it would be nothing and then it would be something. And in this period here, we're getting a very rapid change of current in time. And that causes a very rapid change of magnetic field strength in time. And that means that this is receiving a very rapid change of magnetic field strength in time, which means that we see a current deflection. The current deflection only happens while this rate of change is taking place. So as soon as we get to this steady state, high current flowing through my electromagnet, we don't get any more current flowing. So this is something where this needle will flick when I turn this switch on, and then it will go back down to 0. And it will flick the other way when I turn this switch off. So this will click, this current will appear when I open the switch and close the switch, but not when the switch is always is normally open, which means no current flows, and not when the switch is closed and so a constant current is flowing. It's when it changes, when the current changes, the magnetic field changes. When the magnetic field changes in time, we get an EMF created. So it's a bit weird. Okay, so Faraday studied this, and good old Faraday came up with this basic equation which says the EMF that is induced in a circuit which causes this. We didn't draw it in, but we can imagine a little magnet, a little battery bin created. The EMF that's induced in the circuit is directly proportional to the time rate of change, d phi b by dt, of the magnetic flux through the circuit. And there's a negative sign in there to get the sign right. Okay, it's bookkeeping. I can show you it. We don't justify it. We don't derive it. It's if you like, an empirical thing. Okay. So if we have a coil, this is the thing to watch out for. If there's a coil, always, if I tell you a number of turns, always justify ignoring the number of turns. Don't justify putting the number of turns in. The chances are you're going to need it. You might not always need it. You've got to look at the wording of the question. But the rookie mistake is just ignore the end because it wasn't in the base equation that you learned. But if you visualize it, if this coil, if this loop is having an effect and there's two of them, there should be twice the effect because each loop has the effect. So minus n d phi b by dt. So a coil of wire consists of 20 turns. The magnetic flux through the coil of wire changes at a uniform rate from 8 Tesla to 12 Tesla in 4 seconds. What's the magnitude of the EMF? So first of all, visualize. So I have a coil. So I draw my coils like that, basically. I try and show there's a certain amount of width to them. And basically n equals 20 turns. And the magnetic flux through the coil changes. So I'm going to represent my magnetic flux as like an arrow, just a single arrow. There's a whole family of them, really. That's my flux. It's not my magnetic field. It's my flux. And my flux initial is equal to 8 Tesla meters squared. And then I have another version of this. And my flux final is equal to 12 Tesla meters squared. And my delta T from there to there equals 4 seconds. So I have my coil. I got my magnetic flux. How did I make that magnetic flux? Well, I'm probably going to do it with some kind of magnet. I could talk about the magnetic field strength, but I'm choosing not to. I'm choosing to talk about the most direct thing that affects this, which is the flux, the number of arrows coming out. That's what flux is, number of arrows coming out. If you like, the number of arrows going through that coil is 8 initially, and then 4 seconds later, I do something steadily, and 4 seconds later, it's now at 12. So there's been a time rate of change of flux. What's the EMF? So the EMF is equal to minus n d phi by dt. I suppose we need to have phi b and phi e so that we don't get confused about is it the electric flux versus the magnetic flux. And so we say, okay, so E is equal to minus, and my n is 20. Let's just make this one more step. Minus n. If things stay at a constant rate, then I can kind of do the time averaging thing. So I can make it delta phi b by delta t. And I'm going to do one more step, which equals minus n, and that would be phi b final minus phi b initial over my delta t, I suppose t final minus t initial. Now I look at my question and I say, okay, well, that's going to be minus 20 times phi b final is 12 minus phi b initial is 8 over, and t final minus t initial I don't know, but I know the delta t is equal to 4. So that's going to be minus 20 times 8 over 4. 4 over 4, thank you. Oh, that's a bit of a ropey answer, isn't it? Which is going to be minus 20 volts. And if it's asking for the magnitude of this is just a, don't worry about the sign. It's 20 volts. Cool. So it's just visualization. But you've got to know what flux is. You've got to know what the words stand for. The equation's simple enough in its own right. It's like, let's recall what flux is. And flux is the number of arrows in a given, region, if you like, passing through a certain area. I'll say there's a flux of so many Tesla per square meter. In each square meter, you get so many arrows. It's not equal to the number of Tesla, but it's like related to it. Okay. And I seem to recall that do I recall this? I can't remember. Have we done this before? Yeah, we have, haven't we? So we say flux is equal to the integral of B dot, make sure your dots are clearly dots, times dA. And if I expand that, what that's saying is, take your magnetic field strength, take the perpendicular area, multiply the two together, that's how many arrows you're going to have, basically. Okay, so it's an integral, and it's a dot product because the angle matters. And I know from dot products that this is the magnitude of V times the magnitude of A times the cosine of the angle between. This is a magnetic field vector, and that is an area vector. So again, I have this area vector. I'm inventing this area vector, which really makes dealing with planes very nicely. It's just perpendicular to the plane, has a magnitude equal to the size of the area, a direction at 90 degrees to the plane of the area. If we consider a loop of area A, we get that E is equal to minus d by dt, and rather than putting this phi b in, put in this guy, BA cosine theta. And that leads us to the next thing, which is, all right, we just did a problem on changing flux, but how can we change the flux? And this tells us there's three ways we can change the flux. I can change the flux by changing my magnetic field strength. I can just turn the electromagnet up that this coil is sitting in, Imagine an electromagnet, and I have a coil there in the middle, and I just change the current. If you like, I can get a north pole and a south pole of bound magnets and move them closer or move them further away. I can do that. I can change my area of my coil in time. That's a bit harder to envisage, but you can dream some scheme up whereby you have basically a loop, and maybe you make it a big area, then you make it a small area. You can mess with it one way or another. You can dream some way of changing the area in time. Or I can do what it turns out to be, which from a mathematics point of view, you kind of go, oh man, but the kind of easiest thing to do is to take just a standard coil in a magnetic field. I said the magnetic field is going from the front of the room to the back. Take a magnetic coil, and I just spin it. My area vector moves with a coil, and the magnetic field vector is always that way. So my area vector is in line, it's at 90 degrees, it's anti-lined up, it's at 90 degrees, it's in line, and so on. That turns out to be the easiest way. That's what power stations do. Power stations spin the coil inside the magnetic field, because it turns out it's the easiest thing to do. Changing the magnetic field strength is a real pain. Changing the area of the coil is a real pain. But spinning it's a piece of cake. So that's actually the one that we all use. We spin the coil. But we need to check out that we can do all this stuff, because there's we're learning the full canon of things that can be changed. So a coil of wire consists of 40 turns. Magnetic flux through the coil changes at a uniform rate from magnetic flux. I don't want to do that one. I'm going to change this. Let me just check on that. The coil is in area, yes. This is a mistype on my part. Okay, so the magnetic field through the coil changes at a uniform rate from 2 Tesla to 9 Tesla in 14 seconds. What is the magnitude of the EMF induced in the coil? I got a problem. I need to add a little bit. Assume that B is parallel to A. Otherwise, you got to scale your answer, and it's like. So let's visualize this. I'm going to actually, for this bit, I'm not going to draw a three-dimensional drawing. I'll draw a drawing from above. So here's my coil, and here's my B. I'm drawing B now, not phi. I'm drawing the magnetic field strength. I can figure out my phi from there. Yeah. And so this is N is equal to 40 turns. And there's my area vector A. There's my B. And BI is equal to, I shouldn't have put the arrow head on top of it because I'm going to draw it as a thing. That's 2 Tesla. And here's my magnetic field strength. Now BF is equal to 9 Tesla. And my delta T equals 14 seconds. My area vector is still in that direction there because these are. So I say, oh, EMF is equal to minus N d phi by dt. Phi, B I should put down, is equal to integral of B dot dA. Is it B dot A? It's B dot A, isn't it? B dot A, which equals B A cosine the angle between them, where the angle is the angle between the A and the magnetic field. That is angle between B and A. That's what the dot product says, isn't it? It's the cosine the angle between these two vectors. Which in this case, that's going to equal 0. So put this in. E is equal to minus N d by dt of BA cosine theta. And I know that in this case, let's take out our A because our A is not changing. And let's take out our cosine theta because our cosine theta is not changing. It's only my B that's changing. Equals minus NA cosine theta delta B by delta T. And I don't need to write the whole thing out. You can do this. Minus N, which is minus 40. A we said was, oh, you need an A as well. Oh yeah, because I didn't give you the flux. Okay, so let A equals 2 square meters. And then we have cosine of 0 degrees, because assume that times B final, 9 minus 2 over 14. So E is equal to, that's going to be equal to 1 minus 40 times 2 times 7 over 14. which is 20 times 2, which is minus 40 volts, I believe. That goes into that, which is minus 40 volts. And my magnitude, Emag, is equal to 40 volts. So, works out nicely. Yeah. Now I am back on track. This is a good question. I might have to just be clear about the direction of things. A coil of wire consists of 10 turns. The strength of the magnetic field that passes through the coil is 12 torr. The coil is an area that changes from 3 square meters to 7 square meters in 5 seconds. What's the magnitude of the EMF of the coil? And again, I didn't tell you the direction, so let's assume that B is parallel to A. And I'll talk at the end about if it wasn't, but let's just assume. So I draw it, and I say n equals 10. And then I say, well, this B is equal to 12 turns, and that's 90 degrees. So that means my A is there. And then later on, my B is equal to, again, 12 Tesla. But now my area, I should draw my area differently. It's gone from 3 to 7, so let's just illustrate that a bit better. So this A is equal to 3 square meters, and now A is equal to 7 square meters. And what we say is, okay, let's have a look. Faraday's law, minus n d phi b by dt, and phi b is equal to the integral of b dotted with a, which equals ba cosine the angle between. Those are two vectors. So E is equal to minus n d by dt of ba cosine theta. And then we take out everything that's constant. So we have minus n, of course that's constant. In this case we're not changing b, so b comes out. And in this change we're not changing the angle, so the cosine theta comes out. And that goes dA by dt, which equals minus nb cosine theta, a final minus a initial over delta t. So E is equal to minus 10. My B is not changing, my B is 12. And my cosine theta is cosine 0, which is going to be 1. The way because I put in this little thing there, because I completely forgot about it. And then I'm going to have A final is 7, minus A initial is 3, over time interval. My time interval is 5 seconds. Delta t equals 5 seconds. That's over 5. So that's going to equal minus 120 minus 120 times 4 over 5, which equals minus, let's have a look, 80% of that would be 80 plus 80% of 20 would be 16. So 96, am I right? Yeah, minus 96 volts. And so my Emag is equal to 96 volts. I'm sorry?
The mag is no longer negative.
No, the mag is never negative. Magnitude is a negative. The magnitude just means what's the value of, what's the size of. Positive, negative, doesn't matter for that. Okay. What if I had not said that these B and A were parallel to each other? Well, this cos theta would be a different value. If I said they were perpendicular to each other, then cosine of 90 equals 0, so the whole thing goes to 0. So if I had twisted my coil, let's draw that. If I had twisted my coil so that my B was like that, but I was changing the area of a coil with that orientation, there's no flux going through it no matter what the area is. So I would get a 0 answer for the EMF. And if it was somewhere in between, if it was that, if I was going from, that to that, then I am changing the area, but the area is not the area that I'm given. The area is that bit that's changing. And the way that we can scale our answer from this to that is by simply putting in the value of theta into that. So you basically say, oh look, there's my area vector, here's my B, what's the angle between, and do the cosine of it. So it looks a lot more complicated. Oh, they're not lined up, they're not perfectly at 90 degrees to each other. It looks a lot more complicated, but it's just a cosine term. It's just a scale, it's scaled by that cosine term. So don't let that put you off either. If they're not 90 degrees, it doesn't matter. We tend to, because they're trying to introduce the principle, they tend to get things at 90 degrees to each other because then the angle goes away. But the only problem with that is then later on if you put the angle in, it seems like, oh man, they put an angle in, what do I do now? I'm not used to that, but it's just they're taking a special case when it goes at 90 degrees. So don't overly don't just get blindsided if the angle changes. If the angle is not 90, not if it changes, we're going to do that next, but if the angle's not 90, if the angle's not parallel, then if A is not parallel to B, then just work out the cosine of the angle is fine. So the third little ramification, a coil of wire consists of 15 turns. The strength of the magnetic field that passes through the coil is 12 Tesla. The coil is an area of 3 square meters. The coil between the magnetic field vector, the angle between the magnetic field vector and the coil area vector changes from 25 to 70 in 4 seconds. What's the magnitude? So let's do our B. And that equals 12 Tesla. And then let's do a 90 degrees so that I have an origin. And it says initially the angle between the area vector and the coil vector is 25. So let's draw that in. So there's my A. And if my A is like that, then my coil must be at 90 degrees to that, because that's the way this thing works, isn't it? Your area vector is at 90 degrees to the plane of the coil. And if that's 25, then this here, N, is equal to 15 turns. And A is equal to, the size of it is equal to 3 meters squared. Yeah. Not really, that's a vector should be an IJK. I've been a bit loose with my terminology there, so watch out for that. The vector should be an IJK. I'm just saying the magnitude of this, that mag, is equal to 3. Okay, so now let's take the second scenario. We have the kind of same thing. B is still to the right, and it's equal to 12 Tesla. And now we have 70, so that's going to be much more like that. Notice how by drawing a more representative diagram, it makes my visualization a lot more straightforward. And that's 70 degrees, the angle between the magnetic field vector and the area coil vector is 70 degrees. So here's my A. And A is equal to 3 meters squared. And that's 70 degrees, and N is still that. And my time interval, delta T, to go from that to that, is 4 seconds. So I just turned my coil in 4 seconds. I say, well, let's start with Faraday's law. Minus n d phi b by dt. And I say, well, let's look. Phi b is equal to the integral of b dotted with dA of a. I keep saying dA because we used it like that one time. Which equals b times a times the cosine of the angle between. So we substitute that in and we say E is equal to minus n times the integral of b times a times the cosine of the angle between. And we take out everything that's constant. So E is equal to minus n. B doesn't change. And now A doesn't change. And we have the integral of cosine theta, which equals minus n BA times cosine theta initial minus final minus cosine theta initial over delta t. Yeah, it's delta cosine theta. Oh, dt. Thank you. Did I miss that out further up? No. Okay. Yeah, I'm sorry, I messed up, didn't I? It's going to be d by dt. Let me. I can save the day. I think. No, I can't. Let me. I got into mind. I was just going into mind meld mode. I substitute the wrong thing in. So this is equal to minus n. Bring out everything else that's constant. Well, my b doesn't change. Well, my b doesn't change, and my a doesn't change. So here I have d cosine theta by dt. That's what I should have written. So then let's just redo this bottom bit, because it's going to drive me crazy if I try and just kludge it together. I just put the integral down rather than the differential, but bad. So let's have a look. And I can say that's minus nba. It's going to be delta cosine theta over delta t. So this is equal to, E is equal to minus nba cosine theta final minus cosine theta initial over delta t. So E is equal to minus, let's put some numbers in. So that's n we said was 15. B was 12. A is 3. And we do cosine 70 minus cosine 25 over 4. I get my calculator out. What's the first thing I do when I'm doing trig on a calculator? Check to see that I'm in degrees. And then you're going to say, let's start off with that. So cosine 70, enter, minus cosine 25, enter. I got that bit done. Divided by 4, enter. Multiplied by 3, enter. Multiplied by 12, enter. Multiplied by 15, enter. That gives me minus 76.2, which equals plus 76.2 volts. And so my magnitude, mag, is equal to just 76.2 volts. And I think, as one of the students pointed out, on one of my homework questions, at least one, I put a negative sign here. I just wasn't thinking straight, and I ended up with a negative answer, but that was dropping a sign. Most common mistake, put your teaching hats on. What do you think I see for those people who know what they're doing? So they're not walking into the test not knowing the equation. That doesn't happen very often, but sometimes people, they have a bad day, they don't remember the equations. Really a bad week, because you should learn your equations, before you walk into the test. But let's say that apart from that, when people kind of know what they're doing, but they're going to fall off a cliff, what mistake do you think they'll do? Start, what's that?
Like it takes the angle of 70 minus 25 and then plug it into this.
Yeah, it's not cosine d theta by dt. It's d cosine theta by dt. It's the rate of change of the cosine of the angle, not the cosine of the rate of change of the angle. And they're not the same thing. And, frankly, if you're a speed demon and you like to just do it in your head, and it's just so easy to do that. Because you can, I can just, and they're off. And you got the wrong answer. So slow down, I put down people's times and, first person usually leaves in, an hour, sometimes 45 minutes. Doesn't mean to say that it's bad or good. Actually, sometimes it's really good and sometimes it's really bad. There's no way of telling. When I first started teaching, I thought I could plot a graph of how long people were in the exam room versus what their grade was. Doesn't work. So but most people, there's very rarely I have to wrestle the paper from somebody's hand, So you got time. So slow down a little bit and just write down more steps, and you'll just catch yourself on more things. I'm not doing this because I want to teach you. I'm doing this because I want to get the answer right. And truth, I'm not always good. I'm like, sometimes when I'm writing a test or when I'm doing homework, I will do things in my head because I'm rushing to get the homework up. That's the disadvantage with doing your own homework set, is that there's a semester when you have to do things a lot very quickly. And so you tend to ring the changes. And I'll change this, I'll change that, I'll do this, I'll do that. And you ring the things in your head and you make mistakes. And then the problem is, once they're in there, getting them out is a lot more work than putting them in. So take a leaf out of my book. When I rush, I make mistakes. I wrote the homeworks. I do these. I make far fewer mistakes on this than I do on the homeworks because I'm slowing down. I'm doing this properly. So it's not that. It's just everybody's cursed with the same issue. If you rush, you make more mistakes. So just slow down a bit. Cool questions on that? So Faraday's law, know Faraday's law by name. And that's the next level, I think. There's a level of, do I know my equations? And the next level of professionalism is, do I know them by name? Is Faraday an intimate friend of mine? And so that you can talk about Faraday's law rather than, that equation that does, you can actually talk about. That's the next level of professionalism to go for, is just know them by name.
Just real quick, so if you have that last equation.
Yeah.
Does it matter? All that matters is your change in time and your change in whatever your thing is. But does it matter if it's an uneven change? Like if you have if you have a spinning coil, but at the first quarter turn it's going pretty slow, but at the next quarter turn it's going really quick.
Your EMF, yes, it would, yes. Okay, because we're to make the math easier, we're not using d by dt, we're using delta by delta t. Okay. So we're averaging it out. We're averaging it out over that change. And if you did get an oscilloscope and do this, you'd seen that the actual precise speed does matter. Yeah. And there could be, it's.
So because when you integrate it, it's going to have a different curve.
Because if you integrate over a smaller bit, if you integrate over a slow bit, that's very different from integrating over a fast bit. Yeah. Okay. Yeah. Oh, sorry. The differential of a slow bit is different from the differential of a fast bit. And although you're integrating, we're basically averaging over the whole thing. So I feel like we're integrating that effect over the whole thing, but life doesn't. So let's go on to the next level, and the next thing is motional, not emotional EMF. Some of my students would call this emotional EMF, and I wasn't sure if they were kind of just a slip of the tongue, or whether they were giving me a message, But What we're aiming for is, there's some conceptual stuff, which, and like all conceptual stuff, it's hard. Don't fall into that trap of thinking, oh, conceptual stuff is a piece of cake, because it never is. Conceptual stuff is hard. So there's going to be some equations. So it's not just conceptual stuff, but we're heading towards some conceptual stuff. A thing called Lenz's law, which is interesting. So let's just play with this a little bit. So we have a conductor, piece of wire, aeroplane wings, a conductor, passing through a magnetic field. Well, actually, when you think about it, what piece of metal passes most quickly through the Earth's magnetic field? It's a plane, isn't it? Well, maybe satellites if you go up high enough, but there's not many satellites as big as a Boeing, 747. So when we have aeroplane flying, we have big metal structures going fast through the Earth's magnetic field. So it's kind of interesting. So what happens is, if we think about it from the right-hand rule. So the Earth's magnetic field is, in this case, going into the screen. So, and remember that let's think back. FB equals Q V cross B, and our magnetic field is going into play. Our V in this case is going to the right. So if we point our fingers towards the right, and then we curl our fingers down into the page for the B, V cross B, then our thumb points up the page, and so we'll get a collection of positive charges at the top end of this aeroplane wing. And we have, by analogy, we must be driving a whole bunch of negative charges to the bottom end of the aeroplane wing. And that's a battery. That's an EMF. That's a charge separation device. So that's interesting. The longer I do this for, the more charges I send up there. But there must be some limit on it. And the limit is, the more I separate my charges, the more I get my electric field trying to recombine them. So I got a magnetic system setting up charge separation. I got electric system pushing for charge recombination. And there's a balance between the two. So let's look at that balance point. We say, consider a metal rod that travels through a uniform magnetic field. The motion causes charge separation, so charges build up at the ends of the metal rod. This creates a potential difference between the ends of the metal rod. At equilibrium, the electric force is balanced by the magnetic force. And we know the electric force is Q, the charge of a charge carrier, times the electric field, is equal to QV cross B. Q's cancel, so my electric field, is equal to V cross B. And if I remember that, let's have a look. Remembering that delta V equals E times delta L. I don't remember that from anything, but I do remember this. Isn't E is equal to dV by dx? Didn't we learn that? Yeah, we did learn that. Okay. So remember what the units for electric field? Newtons per coulomb, and electric field is in newtons per coulomb. What's the other thing it can be in? Volts per meter. There's the volts, there's the meters. So rearrange it and we get this. Delta V is equal to E times, not call it delta L, call it delta, don't call it delta S, call it delta L. So we get our EMF is equal to E times delta L, which is V cross B times delta L. You just multiply both sides by delta L, which equals BLV, provided let's have a look. B is perpendicular to L B is perpendicular to V, actually. And I suspect perpendicular to L as well. So this is a highly specialized case, BLV. But what tends to happen in the old English system, because things were done over more time, I remember learning that actually in high school. I learned that. But that's all I knew was that, V equals BLV in this very special case. I had no idea where it came from. And now we see where it comes from. So again, what I keep trying to get across to you folks is, if you've never done physics before, you're trying to take on, it's like you've been given all the food you would have eaten in the last 5 years in like 2 months. And we're saying, eat. Just eat. It's okay. You can eat it. You missed all these food. We're going to make up for that. And you can eat it. And so it's very hard. And so that's why time on task is really important. And it's understandable. I can't do anything about it. It's not that I can just wave my hand and say it doesn't matter, because it does matter. But it's understandable when you feel overwhelmed. And what you've got to do is just, you take half an hour's break and you get back to it, because, you're trying to do a difficult thing. If you've done physics before, again, it's kind of like, it depends how much physics you've done before. My sense is, I think there is a value in learning the simple stuff and then adding the complexity. So even though you're getting it all at once, and you can say, well, this is straightforward for me, so I can generalize to form this. It doesn't matter. I was going to say, but knowing this bit, and then knowing, in the general case it's that, is also an advantage. I don't know there's much difference one way or the other. But either way, when we have a conductor traveling through a magnetic field with a certain velocity, we will get a EMF created, and we can measure the size of the EMF. It's going to be, if they're at 90 degrees to each other, BLV. So a 3 meter long metal rod moves through a uniform 20 Tesla magnetic field at 8 meters per second. The rod's length is parallel to the x-axis. There's my L. The magnetic field is parallel to the y-axis. There's my B. And the rod's velocity is parallel to the z-axis. There's my velocity. And I like to just, y, x, z. Just to remind myself, that's a 3D, like a three-dimensional view. So the rod's velocity.
Yeah, which one is Z?
Oh, I see. It's the European Z. Okay. So, let me just stop for a second. So anyway, a 3 meter long metal rod moves through a uniform 20 Tesla magnetic field, 8 meters per second. So the velocity equals 8 meters per second. There's the orientations. What is the EMF induced in the rod? So we said EMF is equal to, what was it, BLV, and that's what I remember, actually, BLV. I suppose let's just do it, and then I'll talk about that. So that would be B, which is, in this case, I didn't write it down, did I? 20 Tesla. 20 times the length, and the length is, didn't write that down either, did I?
Yeah, 3 meters.
3 meters, man. Times the velocity, and the velocity is 8 meters per second, which is a number. 60 times 80, 6 8s are 48, 480. 480 volts. Now, let's just think for a minute. So we said that E. So let's have a look. We said that this is the problem. QE is equal to QV cross B. Cross your Q's out. And then we said, what did we say? We said EL is equal to V cross B times L. And then we said that EL was equal to V, or epsilon naught, yeah? Electric field times L. So, I could have left this in a more generalized form, but typically, frankly, you tend to get asked the question where it's at 90 degrees to each other. I don't think I've ever been asked the question when they're not at 90 degrees to each other. I could have had this rod kind of tilted, and what would happen then? It would be, so that would be an interesting question, actually. So if I tilted it, if I tilted it like that, then it would affect the, let's just get on. It would affect the dynamics of it, yes.
Which angle is it?
Which angle is it?
Like the angle between the rod and
V,
the magnetic
V
field?
cross B, so it's going to be that angle there. That's the cross product.
So between the magnetic field and the velocity.
Yeah, it's V cross B. But there's also, I think there's some angular assumptions in that bit as well. So. Okay, so now let's play with it a bit more. So let's make a full circuit out of it. So let's take this aeroplane wing and make it into a rolling railroad wheel. So there's an axle with a railroad wheel so it runs smoothly. And put it on rails and then put a resistor between the two rails. So that forms a complete circuit if there's an EMF. And then I move this, allow this railroad wheel to roll backwards and forwards inside a magnetic field, and so I get this motional EMF. So what we say is consider a circuit that has a moving section, a sliding rod, the area of the magnetic field enclosed by the rod, by the loop can change. This induces an EMF that acts like an electrical cell. So the flux through the loop is, flux is equal to BLX. The flux is equal to the magnetic field times the area. So flux is equal to the integral of B dot dA, which equals, well, they're at 90 degrees to each other, B and the, which equals A, and my A is equal to L times X. It's the L, and that's, I'm sorry, that is that L times the X. So there's my A. And that is changing. So we say EMF is equal to minus d phi b by dt, which equals minus d by dt of BLX. Okay. So the EMF is equal to minus b, the L's constant. So it's minus BL dx by dt, and dx by dt equals my velocity. So I get, E is equal to minus BLV. E is equal to minus BLV. Two different ways of getting the same thing. I did one talking about just the rod moving in terms of the magnetic field. I did the other one in terms of Faraday's law. And I get the same EMF in both cases. If the circuit has resistance, then I is equal to epsilon naught over R, which equals BLV over R. Who cares? Okay. So we got this EMF is equal to BLV in two different ways. So it's an important equation, so make sure you know that equation. And then, yes?
But in what case come out negative from one positive
Oh, it doesn't. That's positive, yeah?
and the other one come out negative?
Oh, I don't have a good answer for that. I can't explain that at the moment.
No, you're right.
I just never thought about it.
Or,
Okay.
yeah, Professor.
Yeah.
That's negative BLV, but the previous one is positive.
Yeah, that's right.
That's what he's saying.
I'm sorry, I totally missed that.
Yeah. And it's kind of like I can't give you a decent answer for that.
Okay,
Yeah.
that's fine.
So I'll ask you for magnitude, won't I?
I'll accept that.
They looked at it from the opposite way.
Oh, yeah.
So,
Put a negative.
okay, so that leads us to Lenz's law. And Lenz's law basically tells us about the direction of current flow, which tells us about this sign on the EMF. Okay.
Okay.
So there's two different ways we can look at it. We can look at it from a flux point of view, and we can look at it from a magnetic force point of view. And the key thing about Lenz's law is no matter what you're trying to do, the system will try to stop you from changing. It's a status quo system. So let me just free talk for a while, and then we'll come back to this. If I have let's say I have some kind of coil, and I have a magnet. If I'm pushing a north pole towards that coil, the flux going through that coil changes in time because the north pole's coming towards. that's going to induce an EMF. The EMF is going to set up a magnetic field. If it flows one way around the coil, I'm going to get the magnetic field set up one way. If it goes the other way around the coil, I'm going to get the magnetic field set up the other way. So the magnitude is fine, but the direction is not given by the magnitude. So how do we get the direction? We can get the direction from Lenz's law. What Lenz's law says is, if you're pushing a north pole towards me, I'm going to induce in myself an electric current because of the changing magnetic field, which will tend to stop you from approaching. So on this near end, if I want to stop the north pole from approaching, I do whatever it takes to make a north pole appear at that end as an electromagnet. So it's not the logic, it's just the reaction. So I'm thinking about the coil as being a person and deciding, and that's the way you can visualize it, but it's just a reaction of the coil. If I was to try and pull the north pole away, then the coil would respond by saying, I'm going to try and keep you from moving away, so I'm going to make a south pole here to drag you back. Whatever you do, this thing tries to oppose the change magnetically. Okay. That's one approach. And the other approach is, you look at the change in magnetic flux. The magnetic field is the outcome. The change in magnetic flux are the very arrows that you're going to make the magnetic field from. And the change in magnetic flux can be also used as a feedback system. And that's where we're going to start with. We're going to look at magnetic flux, but eventually we'll look at magnetic field. So let's go to this little loop, and let me have a quick look. Ooh, let's stop here, take a break, and we'll come back in a couple of minutes. Okay. So